Okay, so thank you. Thanks for inviting me for giving this talk. I will try to tell you about inflationary cosmology. Things which I'm going to tell will be, will require some explanations. Just don't hesitate to interrupt me. I slightly changed the title of my talk as compared to what was originally. It's the same thing, but just different inclination. Okay. Oops, just a moment. Interesting. So this is one of the pictures which often appears right now in the literature describing evolution of the universe from very early stages to now. And today is this picture to the right, and to the left is the inflation. So what exactly inflation is in this picture, and why is it necessary at all? You see, it is occupied by maybe 10 to the minus 35 or so seconds after the Big Bang. Very small stage, but it's very important for understanding what is going on in cosmology right now. And to explain the origin of my title is, if you want to explain why inflation is desired, let's ask this question. Suppose we want to create the universe suitable for life, and we want to do it in as simple way as possible. So that's hard task, and that's a hard ask to art of the universe creation. Also, it would be nice to have kind of, if we are engineers, we try to make a foolproof design so that if you change it a little bit, then nevertheless it's going to work. And finally, let's to understand the setting is, let's look at our own universe at present and then play the movie back in time. And that's how usually people visualize the Big Bang. So something banged, and the matter, hot matter, expands in all possible directions. And in a standard hot Big Bang theory, in a standard hot Big Bang theory, assumption is that the total number of particles in the universe is the same from the very beginning to now. That's called adiabatic expansion, almost adiabatic. If we solve all equations together with the data which we presently have, then the part of the universe which we see right now is we can see at the distance, which is approximately 40 something billion light years, which, by the way, immediately raise the question, how is that? Our universe is approximately 14 billion years, but we can see at the distance much larger than that. That's kind of surprising, but let's skip it and move forward. So the size of the universe which we see right now is of the order of 10 to 28 centimeters, and it contains about, the part which we see contains about 10 to the 90 elementary particles, and the total mass is greater than 10 to the 50 tons. So the question is, how is that the whole thing appeared from nothing and then start expanding? What was the singularity? Is it possible to make sense out of it? Okay, so here are some facts from quantum gravity. If we study quantum gravity, it's or GR in general, it's quite convenient to use the system of units where speed of light and h bar and gravitational coupling constant are 1. It's just a rescaling of units. And in these units, many things can be explained easier. In particular, the density of matter in the expanding universe, it's possible to show using Einstein equations for the normal hot matter, that the density of matter was decreasing like 1 divided by time squared. Time is age of the universe. at time smaller than 1, density was, according to this equation, of the order of 1. And that is a dangerous place, because when the density of matter is of the order of 1 in these Planckian units, then quantum gravity fluctuations were so strong, then below that, before this happens, so close to the singularity, we cannot really use quantum gravity and whatever other theory consistently. So far, there are some attempts to study it using string theory. There are some suggestions how we go through the singularity. I will not discuss it right now. I'm just saying that Big Bang theory assumes that this is a picture, okay? So then let's try to understand whether this picture makes any sense. At time equal to 1 in these Planckian units, which is a normal clock, is 10 to the minus 43 seconds. This is Planckian time, and the density of the universe at that time was 1 in Planckian units, or 10 to the 90 something gram per cubic centimeter. So it's Planckian density. At that time, each part of the universe of size 1, we're just trying to reduce everything to something very simple. So if each part of the universe of size 1, which is Planckian length, and which simultaneously is the length, the part of the universe which was able to consistently communicate inside each other. Let me explain what I mean. During Planckian time, which is 10 to the minus 43 seconds, light propagated at the distance 10 to the minus 33 seconds. So this, if I want to say hello somebody, I say, and only people who are at a distance 10 to the minus 33 seconds will be able to see my radio signal sent to them. But if we try to understand how many particles this part of the universe in the very beginning of the universe consists of, the answer is, according to the hot Big Bang theory, it contained only one particle, maybe two particles, maybe five, but not 10 to the 90. So this is, again, not always people were trying to formulate things in the way which, if you look at it, it seemed to be manifestly almost absurd. Because what does it tell you? Right now we have 10 to the 90 particles. At the Planckian time, there was only particle per Planck length, which means that at Planckian time, when the universe, for the first time, you can start describing it using normal cosmology. At the Planckian time, the whole universe consists of 10 to the 90 different regions, which where inside of each you can talk to each other, but outside you do not see your neighbor, because the time was too small. The whole information was only about what was at the distance 10 to the minus 33, and that's about one elementary particle. So if somebody wanted to create the universe, he could make only a very small bang, creating part of the universe with one particle. As for the other particle, he would be unable to approach it because it would be outside of his or her, whatever, its causal region of influence. So the whole idea of creation of the universe, of the Big Bang, assumes that without any special reasons, without any way of communicating and correlating with each other, suddenly 10 to the 90 different parts of the universe, not talking to each other, simultaneously emerged from the singularity. And that's really looks kind of ridiculous. Nobody paid much attention to this fact for a long time because, well, okay, so we are not asking questions about everything to which we do not have potentially any answers. Just our universe was born like that. We study the universe. It's given to us in one copy. We do not ask any questions about properties of this copy. This is something which we study, just like laws of physics. We study laws of physics, and we're not commenting on whether we like it or not. But nevertheless, this is a bit puzzling. So what happened is that we found how to explain quite a lot about what we know about the universe using some very, very simple model, which is called inflationary cosmology. And let me give you first the basic idea. What I will tell right now will be just a little bit of cheating. And I will tell you later what this cheating exactly was, but it helps to understand the basic idea. So suppose you have a large box filled with energetic vacuum. So you have box with a vacuum which has a large energy density. It is quite possible. This is like, for example, what gravitational experiments in the early universe in 98 study of supernova revealed that the energy density of nothing, of vacuum state, which is called also cosmological constant, right now at this moment is not equal to zero. Maybe it's not cosmological constant, maybe it's dark energy, but it's not equal to zero. So we are learning that it's possible to talk about vacuum, which is energetic, vacuum energy density, okay? And then we wait a little bit. And if this box continue to expand, what is inside this box? Because the universe expands. So if there is just this vacuum, then energy density is the same because it's vacuum. You can, for any vacuum, you can give its energy density. But then the box is growing, so the total energy of, well, inside this box grows exponentially. And then you have, this is what happened in de Sitter space. If your universe expands, and this de Sitter space solution was discovered in 1917, long time ago, then the total energy density remains the same, but then Boch and everything goes into particles. This vacuum explodes, it produces particles using the energy which is inside the box. So if the box was growing up in size substantially large amount of times, then we have large number of protons, photons, whatever, proportional to the volume of the box. So how do you make this volume large? Basic idea again. You write down Einstein equations, and one of them in slightly simplified form, when you ignore all matter except for this vacuum, and you ignore whether it's closed or open, I just assume that it's flat universe, it looks like that. Scale factor of the universe, dot. Scale factor is a dot speed of expansion divided by scale factor squared is, there is a typo, is proportional to energy density of the universe. Remove the square in your mind here. It is V0 divided by 3. I've made the typo. It has a solution which expands exponentially growing, inflating universe. Essentially, you say that a dot divided by a is equal to constant. So this gives you exponential expansion, and the constant is Hubble constant. Very, very simple. And then you say, therefore, because the scale factor expands exponentially and the volume grows 3 times more, also exponentially, then the universe eventually gets more and more and more and more energy, however it sounds, and then all of this energy dumps into normal matter, and you get all matter which we need, and that is what was essentially a suggestion by Alan Guth in 1980. So if you have something which he called false vacuum, and then this false vacuum decays and then dumps all of its energy to particles, we can, after having sufficiently large amount of inflation, we can create all of these 10 to the 90 particles of the universe practically from nothing. So it was energetic vacuum, original volume can be extremely small, and then you get everything. And I must say that this idea is not exactly very original. It was studied in its different realizations by different people. One of the first people discussed it was Erast Glynner, who living in Russia, and then he was a war veteran, and he lost his arm during the war, and he was imprisoned, and it was a long life. And he had an idea that maybe our universe must start in a vacuum-like state, and then this vacuum-like state expanded and then produced matter. This was such a weird idea at this time. Nobody really cared about it, and he himself was unable to formulate it in a sufficiently clear way. It was actually the beginning of inflationary theory in a sense, but it was not very far from the level which was formulated by Alan Guth. And then there was another paper by Gurevich, 75. I'm just saying that the several papers where similar ideas were developed, but not to the level of development by Alan Guth, and not to the level of explanation how we're solving many problems of the universe. Why, for example, our universe is so uniform? Oh, well, because we are stretching all inhomogeneities pre-existing in it, and this is exponential expansion which do the job of stretching, so our universe becomes uniform, homogeneous. Why our universe does not rotate? Well, our universe has no evidence that it rotates, but galaxies rotates, stars, planets rotate. Why our universe does not rotate? And the answer is that, well, because it's exponentially expanding. So just like a ballerina, when she spreads her arm, it has the same momentum, but rotation stops if she does this trick. So many things you can suddenly understand using this. And it seemed to be a very simple idea, very clear and must work. But Alan Guth himself have written at the end of his paper, but unfortunately it does not. The universe after this vacuum decays becomes very inhomogeneous. So maybe somebody come and try to help this problem, to solve this problem. So it looks like everything is clear, but you must go in a more deep way into it. In particular, what is the problem? If the universe is really empty, like it is in a vacuum state, how can one tell that it expands? It looks like a philosophical question, but the problem is that if the universe is really in a vacuum-like state, then in de Sitter space, which is determined by expansion of the universe in the vacuum, this de Sitter space looks same in different system of coordinates. There is a system of coordinates describing this is a space where it is expanding, where it is collapsing, or even where it is static. So all expansion does not make any operational meaning if you do not have any dots in space which grow in all possible directions, matter, and if you add matter, then it will be not de Sitter space. So if there is no preferable coordinate system, then there is no preferable time when a vacuum state may decay. And therefore, vacuum decays chaotically, and the universe becomes extremely inhomogeneous. And they were trying to solve the problem. Alan Guth, Stephen Hawking worked on it for a year and a half, and then they concluded that it's impossible to do it. Well, there are some other issues with this scenario. And what helped was to change the paradigm. At first, it looked like, oh, we are talking about almost the same thing, but it was a different scenario. You need to have almost vacuum. So you need to have almost de Sitter. You need to have scalar field which moves slowly. Scalar field is whatever physical field which I will introduce soon. And if it is moving slowly, then the universe expands almost exponentially, and you can just use this mechanism. If, on the other hand, it changes, or anything else, or some other matter changes fast, then there is no inflation. Okay, so there were several models of inflation. One of them, Starobinsky model, was in fact introduced a bit earlier than model of Alan Guth. It Stravinsky did not plan to solve the homogeneity isotropy problem. In fact, he assumed that our universe must start in totally homogeneous and isotropic space. So it was not really a part of the ideology of inflation in the beginning. Nevertheless, paradoxically, it made observational predictions which fit right now, 44 years later. It fits very well to the present observational data. Then there was this model by Alan Guth. He was just slightly later, and as he had admitted that it did not work. And then eventually I improved this model, considering situations where the scale field, which drives inflation, moves slowly. I will explain about this scale field. And if you need to know more about the history, how exactly this happens, whatever, that's a fun story, and I can tell you many fun stories related to inflation if you are interested. But let me try first to cover some material which I wanted. So this new inflation existed and worked until it did not. And in 83, I replaced it by a theory of chaotic inflation, which was much more general and simple. And then there were some other versions of inflationary theory. So let me tell you a few words about the simplest inflationary models of 83. You study scalar field. Well, you know that you have electromagnetic field, and electromagnetic field may have energy. You may also have scalar field. A simple example is a field of pi mesons. More well, popular in the literature example right now is Higgs field, which is, well, some people call it Higgs God particle because it's responsible for so much of physics of standard model. So it is just a scalar field. Well, yet another field. If it is constant, it has constant energy, not depending on anything. If it does not interact with anything, it's just like another vacuum state if it does not move. This simplest theory have energy density related to scalar field, which is proportional to the square of its energy density, of its value. It's very similar to what happens with electromagnetic field. Energy density of electromagnetic field is proportional to the square of the value of electromagnetic field. So nothing special. Now, if you take the simple assumption about the scalar field, then what happens is that in the very early universe, existence of the scalar field, if it was large in the beginning, have led to exponential expansion of the universe. After that, scalar field started gradually changing because it kind of wanted to move down to the minimal values of its potential energy to phi equal to 0. And it is moving down first slowly, then faster, and then it started oscillating and produced normal particles. So let me explain why all of this happened. I'm writing a couple of equations. The first one is this simplified Einstein equation. Hubble constant is proportional to m squared phi squared, which is just potential energy. Klein-Gordon equation describes motion of the scalar field. This equation, if we look only at the first term and the last term, it's very similar to equation of the harmonic oscillator, which say x2 dot is equal to minus kx. So everybody who studied mechanics know this equation. If you add some viscous liquid in which this ball moves, for example, you take a pendulum and put it in the oil, then it will be slowing its motion. So apparently, the equation for the scalar field in expanding universe has these two terms: acceleration of the scalar field, phi 2 dots, and then there is minus m squared phi, which is the potential energy pushing the field down to phi equal to 0. And then there is this friction term, and that's very important term, 3h phi dot. this term is responsible for slowing down scalar field when it moves down from the top of the potential. So returning back here, originally suppose that scalar field was large, then it was moving down, but the Hubble constant was very large because energy was large. Hubble constant is proportional to the square root of energy. Energy was large, Hubble constant was large, friction was large. Scalar field was moving down extremely slowly. And during this time, the energy of the universe did not change much. So we're looking at this equation. If Hubble constant was almost constant because scalar field changing slowly, then a dot divided by a is almost constant. You have exponential kind of solution. Then scale becomes smaller, smaller, smaller. Hubble constant becomes smaller. Then this friction term in this equation becomes also much smaller. And after that, the scalar field just starts oscillating. So if you have this stage at which it was moving slowly and the universe expanded exponentially, this is a stage of inflation. If we have the stage of oscillations, at the stage of oscillation, the scalar field by itself would oscillate for quite a while, but if it was interacting with anything else, then it will be producing particles of different types. And these particles later populated the universe. So this was the way how you dumped the energy of scalar field into energy of normal particles. So you may start with simple semi-realistic models. You may start with a small part of the universe, 10 to the minus 33 centimeter, which is Planckian scale. The total mass of the universe of this type would be Planckian mass, which is approximately 10 to the minus 5 of gram. And then after the time, approximately 10 to the minus 35 seconds, it becomes suddenly this large. And it's so large that it does not matter even in which units it became so large, because it was expanding exponentially, and the size is huge in centimeters, in miles, whatever. It is much, much larger than 10 to the 28 centimeter, which is the size of the universe accessible to observations right now. So if you think about the universe as a cosmic balloon growing, then we would live right now on the tiny, tiny part of this extremely large cosmic balloon, like if we are right now on the Earth and we are limited only by the size of the horizon. We do not see that the universe, that the Earth is round. If we expand the surface of the universe enormously like that, then all mountains will disappear, there will be only plateaus, and that's essentially how inflation works. So it makes the universe absolutely ideally flat, and it makes the universe non-curved because radius of curvature grow large, and it removes all previously existing inhomogeneities in the universe. If you have any nasty things, then you cannot see them right now because they are already outside of your horizon. So that is the idea. Let me stop here for a minute and just ask people, is it what I'm talking about right now? Is it too simple or is it too hard, or whatever you prefer? Because I do not know what are you interested in, what you know about this. Maybe I'm talking about something which all of you already know, and then I can move much, much faster than that. Or if not, if it is complicated, then I may stop here and cover less material, but at least it will be understandable. Do you have any comments? Any of you? Don't worry.
Yeah, I mean, at least for me personally, it's good. You can get more technical. I wanted to ask some questions about your entry into the field, and sort of what you're thinking about. Again, sort of like you mentioned the sort of prehistory of inflation, and it seems to me that the Russian school had all these different calculations and models before Alan Guth. And I was kind of wondering, did that directly, inspire you or influence you? And I was kind of wondering sort of about the timelines, both about when the ideas were first developed and then the specific models that you introduced.
Okay, so then let's change a little bit the plan of the discussion, we will cover as much as we will, but I will tell you, I will describe you the situation how I've witnessed it at that time. So I myself entered cosmology in a rather unexpected way for me. I I was studying particle physics, scattering of neutrino, anti-neutrino with radiative corrections. In 71, I got some prize for my diploma on that in Moscow University. And then in January 72, I went to my advisor, David Kirznets, who was a, fantastically intelligent person, knew quite a lot. And I told him, okay, so shall we publish my diploma? He said, forget about everything that you did so far, because we have right now totally different life, starting from some work of Hooft, who have proven renormalizability of theories with spontaneous symmetry breaking, scalar field, and started asking him what it is. He said, send me to library. And so eventually these theories of spontaneous symmetry breaking, the structure was similar to the structure of superconductivity. In superconductivity at large temperature, symmetry is restored and superconductivity disappears. So let's study analogies between this and what was in the early universe. We start studying it. We found that indeed symmetry breaking in the standard model and other similar models may disappear in the early universe when the temperature was very large, and then it only slowly appeared when the universe was cooling down. And then I noticed that actually when we study this and you have this vacuum, kind of scalar field energy, if scalar field just stays, for example, on the top of the potential in the Higgs potential, how can I interpret it? Well, look at this from the point of view of Einstein theory. You have non-zero vacuum density because you stay on the top of the potential, you do not move. So it is like you do not know even the scalar field is equal to zero in this state before symmetry breaking. So there is nothing, no particles, no nothing. You have just scalar field, which is nothing. It is equal to zero. So if it is a vacuum, then energy momentum tensor of it must be relativistic, some constant multiplied by g mu, and therefore it is a cosmological constant. Okay, so if you have a cosmological constant, and then later the scalar field falls down to the minimum, then this cosmological constant changes. So I've written an article with the title, Is the cosmological constant really a constant? But in Russian, the title of the paper was translated incorrectly. And they translated is the word li in Russian means if. So they translated Lie literally, and they translated this is the Lie constant cosmological constant. So it was totally then screwed the whole paper. But this was I think, the first paper where it was realized that things which we are dealing with in this theory of scalar field is actually deals with vacuum energy, which may change. Then we decided with David Kirznets to study it further, and we studied phase transitions, and we found that sometimes phase transitions from hot universe to not so hot universe may go with a large period of supercooling, and supercooling means that no particles, you have vacuum energy, large vacuum energy, and then boom, there is this vacuum energy decay, and our universe gets slightly more energized because some energy of a vacuum transfers to energy of particles. So we have written an article about this in 74. We sent it to Annals of Physics, but because it was written in the language, my knowledge of English was very imperfect right now, even though it was translated by professional translator. They sent me an article back to improve the language, and altogether, it took 2 years before this paper appears. It appeared in 76. Still, this idea is already there, how you can pump energy from vacuum to normal matter. But what we have seen also during this investigation, that it's very hard to do. You need to have some specific conditions, which at that time looks like really fine-tuning, not warranted by anything. It's 78, together with Chibisov, who was also part of Liberty Physical Institute, where we worked. We studied a model where this vacuum decayed, produced large bubbles, these bubbles collided, and we wanted to check whether this way we can explain why there are not so many baryons. It is baryon asymmetry, only one baryon per 10 to the 10 photons. So we studied and we found that when these huge bubbles collide, then our universe becomes inhomogeneous, and we never published the results. And then Alan Guth did just exactly that. He studied decay of false vacuum. He found that bubbles either collide or never meet, and whatever the universe appears doesn't look like our universe. He admitted it, but he said that it would be interesting to see what happened there, because it would solve so many cosmological problems at once. And I did not know about his work. Before his work was published, I was at some seminar in the Institute of Nuclear Research in Moscow, where they discussed the possibility to solve the flatness problem by these delayed phase transitions. And they found that it does not work. And then I, a couple of months came over, and I received a phone call from Lev Okuny, who was a very respectable physicist studying elementary particles, weak interactions, whatever, and asking me, did you see the paper by Alan Guth? And I said, no, I did not see anything. What is it about? Why are you interested? And he said, Alan Guth is trying to solve the problem of homogeneity and horizon or whatever, using phase transitions with bubble formation. I say, no, I never seen this problem, but let me explain you why it doesn't work. So without seeing Alan's paper, I explained Okuny why it does not work, but it was kind of painful, because the idea, what Alan said, that this is a reason to do it, because you may, if we are able to make it work, then you may solve quite a lot of problems. And because it would be based on the theories which I, during 10 previous years, was developing, it was kind of painful for me that, yes, everybody now realizes that it is so good, that it can be very helpful, and it just does not work. And then the paper by Hawking and collaborators saying that it cannot be improved. And Alan Guth, together with Eric Weinberg, another paper that it cannot be improved. And somewhere in summer 81, I realized that if you have a phase transition which goes kind of not directly to the minimum, which was usually at that time assumed by anybody, but just slightly near the top of the potential, so that the energy density does not abruptly changes, then you may have inflation, exponential expansion of the universe, while just inside the bubble. Not only outside of the bubble where phase transition did not happen yet, but inside the bubble. And then the universe inside the bubble becomes exponentially large. And therefore, inside my bubble, I do not ever see these other bubbles colliding with mine, because they will be exponentially far away. So the idea was very simple, and I actually knew that there is a chance that it might work, because I've studied this tunneling, and I've written a couple of articles about how tunneling goes. And I found that sometimes tunneling may indeed happen kind of almost horizontally, instead of going directly from one minimum to another. So I was very excited, and I called to one friend of mine, Valery Rubakov. He was giving a talk on possibility to solve this horizon problem, flatness problem, using these delayed phase transitions. So I told him, it seems that I know how to do it, and explained him mechanism. And he said, yeah, interesting. I never heard about this before. And then I got really excited, and I waked up my wife and told her that, Renata, I think that I know how the universe was born. So that was about this discovery. This is my perspective. But this perspective is not complete if I will not tell you about Starobinsky model. Starobinsky, quite a while before that, suggested that you can have inflation, we not used this word, but exponential expansion, staying effectively on the top of the potential produced by quantum corrections. And it was a very interesting idea, but in Soviet Union, it immediately became immensely popular. It was discussed at all conferences on cosmology at that time, immediately after it was released. But it was also somewhat incomplete because it was not quite clear what was with the universe before inflationary stage in his scenario. Uh, uh, and it looked like strange thing because for this scenario to work, you needed to sum up contributions of like trillions of different particles, quantum corrections related to that. So it looked like far-fetched idea with why do we need it? The idea of his desire was to solve the singularity problem, and it did not really solve them because of the problem of initial conditions. So what do we do with that? And all answers to these problems, they emerged eventually, but in the beginning, outside of Soviet Union, nobody cared about his model, and then only later people start learning. There was something what Starobinsky was doing, and his model became popular only after Planck data found that prediction of his Planck and WMAP data have found that predictions for his models are very similar to what they find experimentally. Okay, so this was the part of the history from the point of view of Soviet Union. Then after that, in 80, when I invented it, I made my talk in October 81. It was actually quite painful because I had this paper written already in summer of 81, but I needed to get permissions for send it for publication. And this in our system took us about 3 months to get permission. In October, there was a conference on quantum gravity in Moscow, and best people came there. Steve Hawking came, and they gave their talk at this conference. Again, immediate interest. People started asking me, do you want us to smuggle your preprint away from Soviet Union? And I say, no, I just already got a permission and I can send it the regular way. Next day after my talk, I found myself in the Sternberg Institute, which is a part of Moscow University, and Hawking came there to give a talk. And the talk was about inflation. So they asked me to translate. I didn't expect it, but what can I do? And Steve start explaining everyone that old inflationary scenario is problematic, and it's impossible to solve these problems. And usually he would prepare to his talks, so it would come like he was not really giving a talk, his student would give a talk, and Steve just say voila, and the student stopped and then changed it slightly what he was talking about. Still, he was not prepared for this talk, so he say one word, and his student said one word, and then I would say one word, and it was really not a good way to give a talk. Since I knew what is in it, then at some moment I start saying, okay, so this is what Stephen wanted to say, and then I was talking for a few minutes. And then again, Steve say one word, the student say one word, and I continued. At some middle of the lecture, Stephen say that this is you have a problem, but Andrei Linde recently suggested an interesting solution, and I translated happily. And there are best people of Moscow sitting there watching it. And then he said, but this solution isn't correct, and started explaining for half an hour. I was translating why my new inflation does not work. After translation, and I said that I translated but I disagree. We started discussing with Hawking. We became kind of friends. He invited me to the conference in Cambridge. In conference was found eventually by quantum fluctuations produced during inflation in this scenario are too large, and new inflation was dead. And then in '83, I invented chaotic inflation, which was way simpler than new inflation and much more general. And in '86, I found that in simplest versions of inflation, you have also the stage of eternal inflation. So universe start inflating, and then in some parts of it, continuing inflating even as we speak right now. So producing different parts of the universe. Okay, I guess I gave you historical, long historical introduction, even though this discovery of eternal inflation regime was really extremely dramatic for me, at least personally. So if there will be some time later, I can tell you more about this. But we're already 50 minutes into the talk. Okay, so let's go. Just about the principal issues with this. For this scenario to work, we need to get energy practically from nothing, because we start with this Planckian size domain, mass 10 to the minus 5 grams, where energy goes. And there is one thing which people should understand, those who study it, that energy in the expanding universe is not conserved. For example, if it is hot gas and the universe expands, then the pressure of the gas makes some work helping the universe to expand. For the scalar field, the situation is inversed. We have energy of vacuum, and strangely enough, pressure of vacuum is negative. So vacuum, when the universe expands, makes work helping, actually takes energy away from expanding universe. So it's a paradoxical thing, like instability. Exponential instability of the universe filled with vacuum is the origin of inflation. And I probably should stop here talking here about this principle, matter of principle. What I must say something about is a mechanism of quantum creation of quantum fluctuations. So this was tremendously important and very counterintuitive. Most of the data confirming inflation right now are based on investigation of these quantum fluctuations in inflation. Not all, but most quantum fluctuations produced during inflation. And these experiments are confirming inflation. But what are these quantum fluctuations actually? And the idea is the following. So you have quantum fluctuations of all fields, including scalar fields, everywhere. And that's including scalar field, okay? Now, if we are talking about fluctuations in the room, then they appear, disappear, averaging all over them. You live just in normal Minkowski space. But during inflation, you take any wave, quantum fluctuations produced there, and then exponential expansion of the universe makes an exponentially long wave. You take a short wave, it becomes long wave. This is a red line, shows the previous fluctuation was short wave, Now it became long wave. When it is long wave, then equations of motion for the scalar field became similar to what I've shown you, where this term 3h phi dot becomes a leading term. And therefore, this wave becomes kind of frozen and changes together with classical scalar field, changes very, very slowly. Meanwhile, the universe exponentially expands. New waves, which were short wave, which were oscillating, not knowing anything about expansion of the universe, just they would oscillate in room, they became long wave, and long wave fluctuations were frozen on the top of the previously frozen fluctuations. And then new fluctuations are frozen on the top of the previously generated fluctuations. And what we have after a while, you have the first to be frozen fluctuations. They become, they will have exponentially large wavelengths and lots of stuff on top of these fluctuations. So these fluctuations lead to inhomogeneous distribution of the scalar field in the universe. And inhomogeneous distribution becomes responsible for inhomogeneities of density. So classically, universe expands and becomes more and more and more uniform because of inflation. Quantum mechanically, you produce quantum fluctuations, and these quantum fluctuations are responsible for structure of the universe. This is a movie kind of illustrating what happens. So we have more or less homogeneous distribution of scalar field, and then new fluctuations are generated all the time. Each new slide have, however, horizontally exponentially large size because of the stretching of the universe. So what happens, you all the time generate quantum fluctuation of scalar field, and in the valleys here, where the scalar field is small, the distance from one hill to another becomes so exponentially large that you never see these other hills. On the other hand, there are some parts of the universe where the scale of fluctuations just bring the scalar field so far upwards against the laws of gravity, so to say, for the scalar field. Then in these parts, you restart stage of inflation, which requires large field. So the inflation in the universe becomes eternal due to these quantum fluctuations. But from the point of view of observers right now we live already in the place where, like deeply in the valley, we see different parts of the universe, and these quantum fluctuations are reflected in to the anisotropy of cosmic microwave background radiation. So if you go to Florida, watch the launch of the satellites, study the sky very carefully, you will see that the sky is somewhat multicolored, corresponding to the fact that our universe just slightly non-uniform because of the quantum fluctuations. These are the quantum fluctuations are responsible eventually for large-scale structure of our universe. And the Planck goes and produce this map, and then these people from Planck come to me and say, we do not understand it. We travel all the United States, all over the world. We're showing them this map, and somehow nobody is excited. And they say, well, if I go to Home Depot, buy a paint, I will spray the same kind of map for $10. So why anybody would be excited about this? The excitement goes because what we see right now is a photographic plate which shows quantum fluctuations which were produced at 10 to the minus 35 seconds after the Big Bang. So it's absolutely astonishing what they do. And they study spectrum of these perturbations, which means that whether they're large perturbations at small scale or small perturbations at small scale. And they found that they have some peaks there. These are peaks already not they are not peaks of perturbation of scalar field, which disappeared since that time, but they are peaks in the distribution of temperature. And you can predict these peaks in this theory. And this picture shows you a red line, which is theoretical prediction, and round dots are points which experimentally verify it. So experiment and theory match each other very well. The left corner of this situation is more complicated because statistics is not very good on experiments. And there are some stuff about this that observationally our universe is almost flat, which is explained by large stage of inflation. Another thing, NS, is spectrum index of the fluctuations, which shows that perturbations produced in the early universe on a logarithmic scale are almost constant. So they, if we look at the scale twice as large and another twice as large, amplitude of perturbations is approximately the same, but not exactly. So there were two predictions made by Mukhanov and Chibisov in 81. They were the first who studied things like that, and it was done in Stravinsky model. They found that the spectrum is almost flat. Totally flat would be called Harrison-Zeldovich spectrum, but almost flat, not exactly flat. And both of these statements, almost flat and not exactly flat, they're two separate predictions of the theory. And that's what was found by experiment, because simplicity, like if you have something, maybe it should be completely flat, so it would be 1, but it is not 1, it's 0.96, whatever. And this deviation is specific for inflationary perturbations. I better stop here discussing all of these things and how to check inflation in detail, but I will show you this. This is from Planck 2015, and similar, more exact part was presented by Planck in 2018. So what they found and predictions of different versions of inflationary cosmology in comparison with experiment. So my simplest m squared phi squared model, which is quadratic, is way out of this blue area, which is favored by Planck. Many other models, phi to the degree whatever n, they're also out of this blue area, which is favored by Planck. What is shown on this area on the left-hand side is the amplitude of tensor perturbations to scalar. Again, I do not want to go to details of that, but on the horizontal side is the flatness of the spectrum. And the flatness shown about 0.96 or 97, whatever. This was experimental data at that time. And what are these orange dots downstairs? These orange dots downstairs, which are the best fit for Planckian data. I don't say that best fit for everything, but for Planckian data. They are predictions of Stravinsky model, and also something which is called Higgs inflation. I do not have time right now to describe this. And also what you see that the whole area is crossed by two yellow lines. So actually it is the whole region between these two yellow lines can be described by a set of models which are called alpha attractors, and which I will mention later. A few words about Stravinsky model. It's so sad that he actually passed away this year. One of those people who suffered from COVID. Look at this citation index for his first paper on Stravinsky model. Okay, it was invented in 1980, and it was almost no citations. Then it started steadily and slightly growing, but nevertheless his work was not very well known outside of Russia. And then suddenly in 2013, boom, jump up. And that coincided with WMAP data, where in one of the papers they said that it's interesting that our results match so well this model, which was suggested so many years ago. And then Planck data, etc., and the model became immensely popular right now. Okay, but it just shows this gray area shows the unfortunate distinction of what happened when you're born in Soviet Union and your work is not very well publicized outside of the country when people do not travel freely. But also, well, he was stuttering, he was very mathematical, and it was difficult for him to explain his ideas. And his ideas actually changed quite a lot. So this was the original formulation of his model. You have Einstein equation. This is upper line in this. And this Einstein equation on the right-hand side have energy momentum tensor. And he said that maybe energy momentum tensor have one quantum fluctuations for just vacuum. And all of these terms are written here. They are colossal. And to make a model work, they required extremely large coefficient in front of this term, which is very unusual. Usually you would not expect that quantum gravity corrections could be of any significant importance, which was one of the reasons why his model didn't attract much attention. Then later on, but remember, look at this. It is not the way how Starobinsky model is right now represented in the literature. In the literature, it says r plus r squared. This is a different model. It's related, very strongly related model, what he was done in 1980, but it is somewhat different. What is interesting that a study of perturbations in this model produces the result, which is also remains correct in this r plus r squared model. So it was written in the r plus r squared way, to my best of my knowledge, first in our paper with Kaufman and Starobinsky. Starobinsky have written it. We helped him with other parts of work in this paper, but he have written explanation why he decided to drop out this idea of quantum corrections as the origin of this T mu, but instead he just suggested to add this r squared term to the model and explained that he could also add term f function of r, but not many other terms. So this was explanation. And then he said, therefore, the inflationary universe scenario based on this model with r squared term. And here, we shall continue to call this term vacuum polarization for brevity. So in this article, it was also not emphasized much that it is a new idea. It is not just, well, quantum fluctuations, but instead this classical term. But it is a big difference. And then, but the theory of perturbations in this model is practically the same as the one in the previous existing versions of this model. And then something else happened in 85. This was the model which was formulated in our paper. And then later in 84, this model was looked at by Witt, who did not know that this is a Starobinsky model. And he made some transformation of metric and scalar field and represented the model in a convenient way, but not in as convenient way as you see right now in the last line. And this part of the transformation, where you already have canonically normalized scale field plus this potential, it was done already only in 88. So depending on whom you're talking about, they call Starobinsky model is either r plus r squared or this model with exponential potential. Well, so they are indeed related to each other, and they are indeed related to the original Starobinsky model, but they are not quite equivalent. If, for example, I add the potential of a scalar field to the original scale Starobinsky model, and then I try to reduce it to the model we shown at the last line, or if you add the same potential to the theory on the last line, then these two theories will be different. So one should be very careful when you're talking about Starobinsky model, which one of many you exactly have in mind. Okay. Now this is a later stage, which what was happened after 2018, when bicep added to their to the Planck 2018 data, its own data. And what this blue territory, which is favored by Planck plus bicep, it moved strongly down. No yet discovery of any gravitational waves, unlike what Bicep thought in 2014. But instead of that, you have some ellipse where we probably may be living right now. And they said that, look what we're doing. We now firmly ruled out all theories phi to the n, all simplest model of inflation. We firmly ruled out also a natural inflation model, which is shown by purple part of the graph. So this is our results. They take them. Well, so what happened is that they forgot to show here on this graph these predictions of alpha attractors. And on alpha attractors, this is their graph. And these two yellow lines are predictions of alpha attractor T models, and red lines are predictions of alpha attractors E models, which I will explain right now. And if we study versions of these models starting on these phi to the n theories, you'll find something else. That you may start with phi cubed, phi squared, phi cubed, phi squared, 5, whatever. And then in certain limit, all of the theories being incorporated into alpha attractors, they predict the same and they're consistent with Planck and bicep data. So right now in the, I will briefly mention what we're talking about, what these alpha attractors. This is the Lagrangian for the simplest chaotic inflation model with m squared phi squared. I'm doing one small modification. I'm replacing right now kinetic term by a strange looking kinetic term which has a pole here. So if phi becomes equal to something which is called 6 square root of 6 alpha, then you have a singularity there. But this is not a dangerous singularity, because if I go to canonical variables, I will see that this term becomes replaced by kinetic term which looks in terms of this field variable phi looks like canonic term, but the potential becomes like hyperbolic tangent. And interestingly, in this class of theories, you may start with theory m squared phi squared, or may start with the theory whatever potential v of phi, do this transformation, this potential becomes v of function of hyperbolic tangent, kinetic terms becomes canonical, you have this hyperbolic tangent, at large values of the field phi, hyperbolic tangent becomes equal to 1. So starting from when it happens, potential becomes practically constant, your potential develop a plateau, and when you study predictions of this theory, what happens is that all of these predictions depend, predictions measured by Planck and bicep, they all depend only on the height of the potential and on the parameter alpha. They do not depend on anything else. So what does it mean? That you have a large freedom in modifying your potentials, and yet you get the same results. They depend not on the structure of the potential, but essentially on the original structure of the kinetic term and the height of the potential. That's all. Okay, so it's a different perspective. Instead of looking for proper potential, we're looking at combination of potential and kinetic term, and the most important part is actually in the kinetic term. And these are the predictions of a large family of models. If we study this model with many fields, we formulate these many fields, two fields, one sigma and one field, one field sigma is canonical and another field phi is modified, and then you go to canonical variables, then the potentials start looking like that. So in canonical variables, this theory shows valleys, and you can have exponential, slow rolling along the valleys, and after that, you have predictions of all of these models having similarity independently of this chaotic landscape from which you started. So the lesson is that this mechanism makes the potentials flat, which makes inflation possible, which in terms makes the universe flat. So what I'm trying to say is that during last 10 years, there was a lot of progress in engineering of models which fit all the data, which can be implemented in supergravity, not so much in string theory. There are some models where you can do it in string theory, but it's kind of heavy lifting. And I probably need to skip all of these details. This, by the way, this is a planning for CMBS4. Unfortunately, they lost their support for the next 10 years. But similar predictions are for other experiments, which are right now in planning to do. And here is this gray vertical line shows predictions of this family of alpha attractors, and there are some yellow points show predictions of Starobinsky and Higgs inflation. So we are in the business of comparing our models with experimental data. And now I'm going to a more philosophical part. Can we see the moment of creation? Because in Big Bang theory, the whole ideology was if we take a movie of expanding universe and run it back in time, then we will see the universe emerging from the singularity. And if the universe would be transparent, we can actually see the moment of the Big Bang. In inflationary theory, it is not the case. And the reason is that the last important foldings of inflation, which blow up our part of the universe e to the 60 times or so, which makes all the parts of the part of the universe which we see right now, it was formed according to observational data at the energy which is approximately 9 orders of magnitude, at least smaller than Planck density. So the scalar field was rolling, universe was expanding, and right now the structure of our small part of the universe was formed when density was well below Planckian density. And to see what happened at the Big Bang, you would need to have a look at the exponentially large distance, which is practically impossible because you need to wait exponentially long time. And if there is a cosmological constant, then it's actually impossible in principle. So there is a new part of changing perspective about our universe. We look at the sky, we're never going to see the Big Bang, which may be pessimistic because we wanted to know what happened exactly at the Big Bang, or maybe optimistic because from the point of view of theory, inflation is so robust that it does not really care what happened at the Planck density in order to explain what we see right now in our part of the universe. I should talk about this more. After inflation, this was a moment after inflation when all particles were produced, because you start with practically nothing, and then you have all energy in scalar field, and then scalar field produced all particles. So all these 10 to the 90 particles, which we see around, they were produced after inflation, not at the Big Bang. That's how you solve the Big Bang problems. Okay, but then try to run this movie back. You will never see these 10 to the 90 particles converge and turn into vacuum. So this process, process of creation of matter, is irreversible process. It's like when you have a cup fall to the floor, it will never jump back and will never become glued again if it was broken. So it's how second law of thermodynamics works. In the universe, second law of thermodynamics worked in, well, huge degree more than we expected in normal life, because all the entropy of the universe was produced practically in nothing. There was enormous increase of entropy in the universe from maybe a state containing less than one particle, and you get all of these particles. And this is irreversible. If you look at the galaxies which we see right now, you never can make a movie back when these galaxies will glue together and produce a vacuum state. So this is how the picture of the universe differs from what was before. Even before, in quantum mechanics, this 100 years ago was formulated, and now people are still fighting in how to interpret it. You have a Schrödinger cat, and then you have an experiment, and there's some quantum mechanical probability, and cat either dead or alive. And from the point of view Copenhagen interpretation, this means that you're a macroscopic observer, you look at that, and you reduce the wave function to one of the two outcomes. People who like many universe approach, they will say, at the moment when it happens, you will learn in which part of the multiverse you live. So all of this debate about interpretation still continue for 100 years. Now what I'm trying to show right now, this is how it looks for the universe right now and for galaxies. Because for galaxies, the situation is different, because we deal with quantum field theory here. And quantum field theory can produce particles which didn't exist before. In quantum mechanics, you have particles, and you ask questions about probabilities. In quantum field theory, you do not have particles, or you may not have particles, or you may have particles, and how many particles we have in the end, you also do not know. And what we know that in the theory, originally there was no universe. So it's like Schrödinger cat, but without a cat. See? So this interpretation of this is much more complicated, and this shows that actually to have a consistent picture of the universe which surround us, we need to live with understanding that macroscopic objects like galaxies could have been produced by quantum fluctuations, and you cannot reproduce the origin of their creation by going and saying there's something splitting or something pre-existing into them, some organization of matter which was inhomogeneously distributed in the early universe. No, it does not work. All models which exist at the moment, which describe the observational structure of the universe, are based in one or another version of this quantum mechanical process of creation of galaxies. Well, and finally, I will talk about something else. Dreams of a Final Theory. This was something which was written in the Einstein autobiographical notes in 1949. He said that I would like to state a theorem which at present can be based upon anything more than a faith. Look how it sounds. A theorem which is not based by anything but a faith. In the simplicity, intelligibility of nature, there are no arbitrary constant. Nature is so constituted that it's possible logically to lay down whatever. So you may be able to read all of this stuff in the recording, but the idea is that it would be great to understand that the way our universe is organized is because of some underlying principle which we physicists are trying to uncover. And that's what people are trying to do all the time. They are trying to find, say, they succeeded in finding this standard model of elementary particles unifying weak and electromagnetic interactions. SU3 like a symmetry of strong interactions. So they try to simplify and organize existing knowledge with the idea that eventually everything will be so organized that everything will be explained. And we were living in this with that idea for quite a while, but then what happened is that inflationary cosmology actually is at certain odds with what Einstein wanted. So some of the constants which we see right now may be not fundamental, but maybe environmental. And I will try to explain. So uniformity of the universe is explained by inflation because of exponential stretching of the universe. But the same theory, because it is also responsible for creation of huge quantum fluctuations, make the universe 100% on the very large scale, 100% non-uniform, divided into different pieces. So the universe, even if it starts unique, it becomes a multiverse. This is a simple example illustrating it. So if you take a ball which expands, then inflation blows it up. If you were born in the blue region, then the blue region is so exponentially large that you will never see its boundaries. Yellow region is so large that you never see its boundaries. So you think that our universe is a universe, and you live in this universe. No experimental data suggesting that black universe exists. But if you start with this ball with multicolored stuff, then finding only blue is not a proof that we live in the universe rather than in this multicolored multiverse. So pessimists would say, if each part of the multiverse is huge, we will never see other parts, so it's impossible to prove that we live in the multiverse. Optimists will say, if each part of the multiverse is huge, we will never see other parts, so it is impossible to disprove that we live in the multiverse. And the question is then, what is fundamental? And Einstein said, I would rather be an optimist and a fool than a pessimist and right. So the point is that the scenario where the universe consists of many different parts, exponential large with different properties, is more general. And if we say that our universe is really universe, this is something very specific, and one should come with a proof of this concept, and there are no possibility to find such proof. Example why it may be important. Supersymmetric SU5 model. It has many different minima in symmetry SU5, SU4 cross U1, whatever. And potentially this model is of 80s. Okay, potentially you may live in SU5, SU4, SU3, whatever, except for you cannot really live in SU5 because particles which are necessary for us, they are described by a standard model. Why then we live in this green minimum? And there was a discussion about this long time ago, and there was a problem. And then if you have inflation, quantum fluctuation can throw you out from one minimum to another. And then the universe becomes divided into pieces, to red pieces, blue pieces. This is a result of computer simulations. Okay, pieces where physics is different, where you belong to one minimum, another minimum, and you must live in the green minimum, and maybe even the volume of green pieces will be smaller than the red, whatever, but you cannot live in red, you cannot live in blue. That is why you see yourself, we see each other in this green minimum, but there may be other minima, and this is a generic picture, okay? So this allows to justify the anthropic principle. We live in those parts of the multiverse where we can live. And this became especially pronounced in the context of string theory, where, according to some old theoretical estimates, the universe may have like 10 to the 500 different vacua with different properties. This is 10 to the 500 or 10 to the 1500, or maybe even infinitely many, or maybe none. We do not really know, because the theory is extremely complicated. And since this will be first ideas how to stabilize string theory vacuum in KKLT scenario in 2003, 20 years people are still fighting what is possible and what is impossible in string theory. But the idea is out of the, it's like people say, genie is out of the bottle, and put it back to the bottle is very, very difficult. You have a possibility in principle that our universe may exist in many different states. And this is the only presently available explanation of why vacuum energy is so small. Because you may have these billions of different minima of vacuum, and look at the left part before we start calculating quantum corrections to potentials, and the right part after you start calculating quantum corrections. These potentials may differ substantially. Quantum corrections in the vacuum in which we live right now, you must live with a cosmological constant smaller than 10 to the minus 120. For those who are interested in a history of this subject, this history is slightly different from my perspective to what you can find in the textbook right now. In 1984, actually in 1983, I was traveling to Gorky to visit academician Sakharov, Andrei Sakharov, who was a famous Russian dissident and one of the author of the hydrogen bomb, fortunately or unfortunately, whatever way. And he was in exile in Gorky. So I was visiting him there, and I was talking with him about this multiverse thing. And I was telling him about the scalar field and other versions of the theory which allow to affect cosmological constant. And he started thinking about different types of compactification in theories with spontaneous compactification of extra dimensions. So in the beginning of 94, I have written an article published where it was written that if you have certain type of tensor fields which kind of simulate cosmological constant, and these tensor fields have a property that once their values are fixed, their values are the same for the whole universe and never going to change. Then I said, we'll study quantum creation of the universe. And in quantum creation of the universe, the wave function of the universe must cover universes with all values of this tensor field. And therefore, in some of them, there will be entropically acceptable, because if cosmological constant is too large, then the galaxies are torn apart and do not form. If cosmological constant is negative, universe collapses too fast. So we can live only in this band where we can live. With the interval about a couple of months, Sakharov published a paper saying that in different types of universes, you have different type of compactifications. And because we have many different types of compactifications, the total number of multi-dimensional of compactifications in a multi-dimensional universe must be exponentially large. Therefore, cosmological constant in different parts of compactifications may take different values. And that also, because of anthropic considerations, explain this, gives a solution of the cosmological constant problem. So from my perspective, this is the idea going to these two papers of 84. In 87, Weinberg actually derived accurately the reason for this bound on the cosmological constant about this formation of galaxies, which is forbidden if you're far away from the bound. So this is right now the solution of the anthropic solution of the cosmological constant is mostly ascribed to him. And in a sense, he made a very, very important step, and his subsequent works were also very important for that. But the history of this idea goes way back in time, and nobody cared about it at all until 2003, where this idea of different types of compactifications in string theory was proposed. And after that, you have this multiverse, and everything became discussed by many string theorists, etc. I would not claim the total victory in this respect. I'm just saying that this is a different way of thinking about problems, and these different things, way of thinking can be quite fruitful. I'm going to finish my talk in 5 minutes. So let me tell you something which I found when we were in the Leiden in Netherlands for 3 months. There in the institute, at every corner, there are photographs of Ehrenfest, who is right now in the middle of this picture. And he is surrounded by De Sitter, Lorentz, Eddington, Einstein. Everybody there tell us about the tragic fate of Ehrenfest, and it's really horrible, the house where he was living, etc. And nobody knew about his work of 1917, same year when De Sitter discovered De Sitter universe. He have written a paper saying that in space-time of dimension d greater than 4, planetary systems and atoms are unstable. It's just, well, at dimension larger than 4, then Coulomb interaction decreases like 1 divided by r cube or r to the 4, whatever. With all of these types of interactions, planetary systems become unstable, atoms becomes unstable, so we cannot live in spaces with d greater than 4. At that time, he did not know yet, but now we know that in general theory of relativity, in d smaller than 4, there is zero attraction between far removed bodies. Like if you have two stars in d equal to 2 or 3, they do not interact gravitationally. There's some special features of the Einstein theory. As a result, we can live only in d equal 4. So if you look at it, who cares? Because we know that we live in d equal 4. Why we consider this nonsense? But the reason is that in string theory, it can be d equal 10, it can be d equal 9, 6, whatever, and 2. So this question becomes a question of physics. Why we live in a space where 6 dimensions are compactified rather than 5? And people are trying to find this reason or that reason, etc. But here is an obvious reason that there could be different types of compactification. But we do not say that our universe is the best, but this is the only place which is compatible with our existence. And well, inflation or exponential expansion of space may explain why there are so many of them and why they may have different properties, etc. So this is what is here in this text. Can we test the multiverse theory? And you can often find again in popular articles describing it that, but it is untestable theory, because if our universe is so large that we cannot test it, really, I would say that here one must use a logic of a different type, which was suggested by this great philosopher. When you have eliminated the impossible, whatever remains, however improbable, must be the truth. So if you tried to find an explanation of a cosmological constant, this way or that way, you failed. If we try to understand why proton mass and neutron mass are similar to each other, equal actually to each other, with an accuracy greater than 1%, what is the mystery? Why there is such a fine-tuning of masses? And the answer is that, well, no, physics really doesn't give you an answer. But what you know, that if it would be a bit greater, like for example, neutron is more than 1% heavier than a proton, then neutrons would decay into protons, and our universe would consist only of protons and electrons, so at maximum they will produce hydrogen. We cannot live there. If protons 1% heavier than neutrons, then protons would decay, and the only object to exist would be neutron stars. So you have lots and lots of explanations of observational facts, which can be explained only if you have a choice. Because without choice, if the mass of the proton is a constant of nature, then you are there, and then you have a mystery why this constant of nature for proton and neutron are the same. If you have a choice, like in the multiverse, then you say, I understand the answer. possible answer. So we need to learn how to use these tools because they are controversial tools. It's just once we got the tools, we need to learn the rules of the game. And I will finish it with something which may seem completely ridiculous. Albert Einstein asked a question saying that the most incomprehensible thing about the universe is that it is comprehensible. Okay? Why the universe obeys rules of mathematics? This was later repeated by Eugene Wigner, who said that unreasonable efficiency of mathematics and science is a gift we neither understand nor deserve. Israel Gelfand said that the only something opposite. There is only one thing which is more unreasonable than the unreasonable effectiveness of mathematics and physics, and that is the unreasonable ineffectiveness of mathematics and biology. Whatever way, for each of them, success of mathematics was unreasonable. But now think about it. What is the reason why it was sounding so surprising? Because uh, because why? If the universe was everywhere the same, it was just created in one copy, and this copy was so lucky to have advanced mathematics, which worked so well to describe whatever. This is just a gift of God. Probability of that would be close to zero. But if you have an inflationary multiverse, in inflationary multiverse, there are parts where density of matter right now is close to Planckian. If you try to build any recording device there, it is broken because quantum fluctuations are too large. In the part of the universe where energy density is negative, then you cannot build any devices which remember anything because they are going to be broken because the universe would collapse nearly instantly. So we live in a part of space which, because of their properties, in part of the multiverse, where you can form stable structures, where memory can persist, where you can engineer these structures. And these structures are essential for us to win the game of the evolution. So we can live only in the parts of the multiverse. We, physicists and mathematicians, can live only in parts of the universe where physics and mathematics are so efficient to allow our life and survival. And therefore, the picture of the universe looks like that. This is a multiverse which consists of parts producing new parts, up to infinity. And physicists can live only in those parts of the universe where mathematics is efficient and the universe is comprehensible. With that, I am finishing my incomprehensible talk. Thank you.
Thank you very much. Yeah, so for if anyone wants to ask questions, please go ahead. Actually wanted to ask about the KKLT scenario that you mentioned. And I was wondering if you had any comments on sort of the recent work of McAllister and others.
Good. Okay. Well, this is much better than the work is much better than it was before. You can always find some reason to believe or not to believe in anything that people say. Like people who want to criticize string theory in general, they may say some words which I have heard, but I would have difficulty to interpret them fully. It sounds like that. String theory was formulated on the two-dimensional world sheet, and there you could prove its UV finiteness and everything was good. But then you needed to describe a realistic universe to add there something which was not a part of the original idea, which was Ramon forms and everything else. And then in this combined theory, actually, it was not, to my knowledge, ever proven that the theory is UV complete and consistent, etc. But sometimes you may find approximations which are good enough and may be justified one way or another. So we are dealing with a building which is still in the process of being constructed. Their paper probably is the best which is written to the moment, which is, well, works in the direction of justifying KKLT construction. Whether it is completely convincing or not, they themselves say that there are some issues which we wanted to study more, and this in particular, we sent a message to them mentioning this problem which I just mentioned, and they argued that in their procedure there is some particular reason why this particular problem should not, they hope, affect it, and they continue their work. So this is a work in progress, but this is much more detailed investigation than what we had before.
Yeah, thank you for answering. It seems, at least to me, just taking a cursory look at, very, very technical issues. I remember with the KKLT paper as well, there were some criticisms and comments on like the anti D3 brains and the uplift and all that kind of thing. And it seemed to me, up in the air of what people wanted to investigate more and people accepted and so on and so forth.
Yeah, what I can say is that it is interesting and maybe telling that the KKLT scenario was suggested in 2003. I must say that my role in this was mostly in terms of cosmological investigation and also the study of tunneling from one vacuum to another. I'm less able to be responsible for string theory per se, but what is quite telling that it took 20 years and there is no ironclad definitive statement in either direction. There was a criticism, and there was a criticism of the criticism of the criticism of criticism of criticism, and so far we do not know. What we know, however, there are some alternatives like put forward by swampland conjecture. They're saying that it's absolutely impossible to have any string theory minimum of potential which can be stabilized. But then they suggest that, okay, but maybe there is sufficiently flat potential. Then they suggest this kind of flat potential is almost good enough to flat, but no, to the best of my knowledge, no good theory of dark energy, which was suggested in this context in string landscapes, sorry, in the swampland, which would be consistent with the swampland conjecture was so far proposed. After they came with their conjecture, we have written our long report saying, explaining how difficult it is to produce it, to justify many of these conjectures. One of them at least, Trans-Planck conjecture, I believe is just incorrect for some physical reason. So it's a game, and what happened also, you may, if you look at the string theory conferences, well, there are not so many, to say the least, talks about string theory proper, okay? And the latest conference, maybe this one paper was the one most related to the string theory proper materials. Everything else was about swampland, about maybe quantum information, or some other things. And there were lots of questions about this, and some of the questions which was asked by, I don't know, I remember who, was what we're going to do when the experts in string theory will retire, and who will teach us why something this or whatever. So people are not very sure about where we stay right now. they move to other directions where they can get more definite results. So what is important for me in this, nevertheless, there are some issues which are related to technical statements, but there are some other issues which are more general in their formulation. And one of these questions is indeed about the multiverse thing, because it's do we know that actually the final theory is a string theory? I don't know really. Maybe just like with gravity, we have some limits of Einstein theory, we have some limits of the present ideas. What, however, appeared as a result of all of these discussions is the possibility, a real possibility, not something, but in a reasonably good models, you have a possibility that our universe may have enormous amount of different vacuum states. In fact, this possibility was raised well before KKLT scenario. It was in year 1986, maybe even 85, when a group of people uh, uh, have written a set of papers trying to quantify the total number of consistent, well, at that stage, solutions of string theory. And they were puzzled by their multiplicity, but they did not find any well-established minimum, but they were talking about the numbers like also 10 to the degree 1,000 or something. And when I've seen their papers, in my own paper on eternal inflation, I finished the paper by saying that, well, this situation which we have right now in eternal inflation, we see that the universe jumping all the time, and fluctuations produced there are so strong that they can bring us from one vacuum to another, from one solution to another. And in this sense, the abundance of solutions in string theory is not its defect, it's virtue, because it allows us to understand from a different perspective the properties of the world where we live in. So it was in 86, and at that time nobody cared about what I said, because anthropic principle was really considered like, oh, this is so horrible. I myself considered it horrible until it was shown that it can be, in fact, implemented consistently in physics. In inflationary cosmology, you can find it. You can forget about string theory. You can study this SU5 supersymmetric theory, and you find dozen of different minima there. So then you ask a question, why? You can forget about string theory. You study theory of axion, just normal axion, okay? And this normal axion, it has a tiny mass during inflation. It was spread, taking different values in different parts of the universe. And in some parts it may be large, in some parts it may be small. And then in the parts where it was very large, then you have large dark dark matter. In the parts where it is small, there will be a small amount of dark matter. So you have in the same universe, without any even jumps, whatever, just statistically fluctuating axion field, you may have a universe where you have different ratio of dark matter to normal matter. And if you study process of production of baryon asymmetry in Affleck-Dine scenario, then it depends on CP violation, which is a function of some parameter, which is by itself a field. And therefore, the universe may be divided into places, which one of them are filled with antimatter and one with matter, and we live in our place. And with okay, so I may continue. I'm just trying to say that there are some different ways of thinking about the universe which emerged at the place where inflation goes together with string theory, goes together with other branches of modern physics. And this is something which we still need to learn how to work with.
Yeah, thank you very much. I find it very interesting the timeline because to my understanding, and as what you were saying, a lot of people thought that the cosmological constant would be exactly zero for
Yeah.
various supersymmetric or otherwise reasons, and
Yeah.
there was a lot of sociological belief in that, but it was kind of shattered. And from yours, it seems like your point of view is from thinking about inflationary cosmology, and a lot of people weren't really doing that at that time.
Yeah, as I said, there was a paper before our paper with our papers with Sakharov. There was Paul Davies, who also suggested anthropic justification of the cosmological constant. It was, I think, maybe in 82 or something. I don't remember exactly the date, where he also said about well, the fact that we cannot live in this space with large cosmological constant. So qualitatively, the possibility to explain present value of cosmological constant by anthropic consideration was known. But in the paper by Davis, if you really look at physics of it, then his model would not work. Okay, so that is why I was looking for a model which actually worked, because the idea was transparent, and the constraint that the value of the cosmological constant is anthropically bound in some band. uh, for those people who were thinking about it, it was obvious for me and Sakharov, but we did not know the numbers. So what was done by Steve Weinberg, he actually studied this in detail and make a convincing case that there are some physics behind this constraint on the cosmological constant. But he did not suggest at the time any realization, physical mechanism which would allow you to have multiverse with different values of cosmological constant.
Yeah, thank you. Are there any other questions?
Yeah, I was wondering if you could expand a little bit more on the alpha attractor models, kind of like how they fit in, kind of on their motivations in their sort of like formulation, and kind of how that fit in with like the experimental data at the time.
Okay. Let me go back to these alpha attractors. Actually, the history of all of alpha attractors was also kind of funny. Uh, we had this Starobinsky model, and the Starobinsky model is just perfectly occupied the well, low part of the picture. And nobody cared about this, as I said. For many years, Stravinsky model was not very popular. And then suddenly his model and the model of Higgs inflation, which was in different time rediscovered by different people, but also pretty old. Uh, so these two models are in a perfect position in the graph, and many other ruled out. How is that? What is the reason? And then we start looking at these models, and we have found that it's possible to generalize it and to understand the origin of it. So if you look, for example, to the Stravinsky model, I think that maybe I will find something here. Okay, look at this Stravinsky model. It was r plus r squared. Okay, so let's start with that. This was the model. You don't see here anything specific there. If you add the term r cube, well, suddenly the predictions may change substantially. So what is the interpretation of this model? Then you do two things. First, you change your metric. And after you change the metric the way I've written, this r squared term disappears. It become absorbed, and this was done by Witt in 84. This term becomes absorbed into a scalar field. So you have extra degree of freedom in this theory, not just gravity, but scalar field. R squared, on the other hand, in the way how it is written, if you have large R, then essentially it renormalizes a coefficient which was written in the first term with R. So it was the original model was hard to interpret. The coefficient standing in front of R was not really a Planck constant because it also depends on the classical value of R. So when you make this transformation, you went to Einstein frame, and in the Einstein frame, everything becomes cool, but the scalar field is non-canonical. So you have a theory with non-canonical field. It's difficult to interpret. And then this group of people, Barrow, Maeda, etc., they made a second transformation, and they made just solve equations. And in the solve equation, this field was kind of looking singular or strange. Then it is transformed into a theory where everything is regular. Okay, and then we studied the Higgs inflation. And in Higgs inflation, the story was the same. It was the theory Einstein plus R multiplied by R multiplied by phi squared. Same like in Stravinsky model, you can avoid this interaction R multiplied by phi squared if you make a transformation of some variables. Again, in the process of eliminating this extra term, you have some singular term in the kinetic term, and then having this eliminated this term, you have this potential which is having like Plato. And then the way towards this model was also interesting. In our study of supergravity inflation a long time ago, I learned from Renata and from other people on supergravity about superconformal approach to supergravity. It looked like something, well, I did not prepare the slides to show you. It looks like something, okay, people in supergravity, they work using this approach for ages because this was a convenient tool to formulate inflationary theory in the most, phenomenological supergravity in the most convenient way. So I have added some extra field to the theory, which we called conformon field, which is a part of the theory which just like auxiliary field exists something additional field, and then the theory is invariant with respect to some transformations which may affect the value of this conformon. And when they fix this conformon to be equal to a constant, then this constant becomes a Planckian constant. Before you fix it, Planck constant, gravitational constant, is, well, just something not well defined. After you fix it, and this is just a choice of gauge, if you wish. Okay, so after you fix it, you have normal supergravity. So way towards normal supergravity often goes through that. So I asked them to teach me what kind of stupid models which I can extract with it without supergravity. And they start telling me something, I start learning. So we have written a Lagrangian, which was R minus d phi squared as normal theory, minus m squared phi squared. And then I added to, actually, this was a part of their construction, minus some additional field chi squared, whatever. And you create a theory which has this extra conformal invariance hidden into it, which, however, after you eliminate this conformal field, it becomes a normal theory without any ghosts or anything. So I looked at this construction and I found that you can easily write a theory where you can add this conformal field in such a way that after you eliminate it, you will find a cosmological constant. That was already interesting. And then what do you do in order to get a potential? And then we did another trick with this theory, and we get a potential which was hyperbolic tangent. So that was the beginning of this, and this was only because we were excited by Planck result saying that no non-Gaussianity, you have a way to go, and this way goes in the direction possibly towards Starobinsky model and Higgs inflation. So we start thinking what is the reason, and we immediately found another class of theories. And then after that, we worked more, and then we found this other class of theories. So everything happened within 1 year after the first Planck data release in 2013. We started working on theories which were interesting at that time, because previously all people were preparing for the disaster that you have large non-Gaussianities. Large non-Gaussianities rule out all single field inflationary models, and then no non-Gaussianity. And when we realized it, that we do not have any danger, we can really continue trying to understand how to construct models of this type. We have found it, and some parts which I did not have any time to show. When you have a complex scalar field, then this is equivalent of, well, using Poincaré disks and very nice mathematics related to these Escher paintings. And this is how I illustrated this on this theory of m squared, phi squared potential with all of these angels and demons occupying upper part of it. So this was a really very interesting way of thinking, and I mostly learned most of it way of thinking from my wife Renata Kalish. She started studying in the middle of our work. She started opening some websites and checking what Escher did, and I said, "What are you doing? Let's continue what we work." No. She continued studying these Escher websites, and then we had our alpha attractors.
Thanks.
Okay. Okay, so if it's all, then, yeah, anything else?
Oh, go ahead.
Like in internal inflation models, what are the specific features of different models of what the inflaton field could actually be? For example, you mentioned at the start of your talk that it's a scalar field like Higgs. Is it usually considered to be like a condensate that associate with some early phase transition? Because I don't come from physics background. I come from like more math background, so I don't know if it's a correct way to think about it. And what are the implications of like different energy scales of inflaton field? Like, what do they lead to as like consequences in the like multiverse?
Okay, so first of all, in this theory, just like in everywhere in particle physics, you can introduce lots of different fields, including scale fields, and all of them may have different energy scales, etc. This simplest model which I described to you, which is, by the way, shown by this paraboloid, it does not have any particular energy scale. It goes from 0 to the Planck energy density. However, if you look at the original original picture of it, which I've shown, this picture by itself, okay, here we go. Okay, this picture by itself shows you when different things happen. So when you are close to Planckian density, but still many orders of magnitude below it, okay, this is the area where quantum fluctuations are so large that they can bring you upstairs. And essentially, let me explain what happened. You have a piece of space, and this piece of space expands. And during expansion, it also produces quantum fluctuations. So this quantum fluctuation may push the field upwards and may push the field downwards. So let's consider a part where by chance push the field upwards. Now, if they push the field upwards, this part has larger energy. It starts expanding faster. And then it's not very probable, this process, but when you are pushed upwards, then you start expanding exponentially faster. And so you ask questions, even if the persistent jumps up are very improbable, but if you are rewarded by the new areas of the universe produce it in the process, maybe this is how it is. In some parts and in most points in the universe, you jump down, but the main volume of the universe is produced by the areas, by the points which, against all normal logic, jump upwards. So this was pretty weird. This mechanism is quite general. A very similar mechanism actually was discovered by Alex Vilenkin in 83, 2 years earlier, where you study inflationary potential, which has a top, and near the top, you can jump down and slide down, and there will be end of inflation. But you may also jump back to the top. And these parts which jump back to the top, they can continue inflation. What was surprising for me in this picture, that you are not even having any top. You may jump upwards and upwards and higher to the Planckian density. And this, well, nobody can forbid it. Or at least we do not see any, I do not see any reason why this process would be impossible. And this was in 86. Since you kind of asked me questions about the history, if we have 2 more minutes, I can tell you the history, how all this happens, because it was really weird. Do we have 2 minutes?
Oh,
Yeah,
yes,
please go ahead.
Okay, so it was 85, and chaotic inflation was invented. Properties were known, and more or less it became clear for me that, well, I'm ready to write a book. Why not? The theory of inflation was well formulated. General community did not yet know about this. Why not write a book? And I started writing a book, but I hated it. Because, you know, I did not like to repeat everything that was in different papers. There was no computers, paper. Well, okay, I didn't like it at all. Then, in addition to that, there was a new thing. In 85, Gorbachev came with his perestroika. And one of the first things they did, we have this complicated procedure of applying for permission for publication, which took few months, etc. So they decided to reconstruct it in a better way. And the first act of reconstruction was to demolish the previous system of getting permission. And the reconstruction took a lot of time. So for about a year, we were unable legally to send our papers abroad because this agency didn't exist. So we're living in a mouth shut. Then, on the other hand, we had enough money to buy a small car, which was important for us at this stage. We were living far away from the institute. And we learned how to drive the car. So it was very unpleasant when your instructor told you everything he thinks about you, idiot, because with my already grown up instincts, I did not know how to drive the car on the Moscow ice. So in the end, I found myself in the state, maybe which I explain right now, like depression. I was laying in the bed, I was reading detective stories, but I was unable really to function well. And then there was a call from my institute saying that you must go to Italy to give lectures on astronomy to, well, citizen of Rome and Turin, whatever. And I said, no, I cannot, I am ill. Because at that time, the maximum allowed us to go abroad once. And spending this once for giving popular lectures of citizen of Rome, this was not my best idea of having it scientifically valuable. So I say, I'm ill. They say, no, if you are ill, send us certificates showing that you're ill. Renata went to Lebedev Institute and asked Ginsburg, who was that head of our theory division, can you write something certifying that Andrei Linde is ill, cannot go to Italy? He said, oh, it's so easy not to go to Italy. He just does not go. But he have written it to her. Couple of days later, there was a call saying that, well, today you are ill, but tomorrow you will be healthy. Apparently, there was something about Russian-Italian friendship. They never asked us to go abroad. Usually you beg them to go to a conference, and this time they asked. And they said, no, I really feel very bad. Are you telling us that you just cannot go abroad, period? And that was sounding really dangerous because it was so easy and multiple examples around when they just said that this person never go abroad, and that was it. No meetings, no conference in other countries. So I got scared. I took a taxi, which was at that time a financial decision for me. And I went to a hospital of Academy of Sciences. In one day, I went through all doctors and get a certificate showing that I am perfectly healthy. I returned back without, any strength, got to my bed. It was Saturday and Sunday. I was working during that time, preparing my paperwork. On Monday, I wake up, I took a taxi, paid again, went to the Lebedev Institute, paid to the secretaries to instantly type these, documents required for them to allow me to go abroad. And I signed it everywhere in the institute. Usually, this process takes about a month, but I was so scared. I went to every corner, grabbed every possible person. I was able to finish it within one day. And I returned back, and I was laying in the bed for a couple of days, really without any strength. And then there was a call from Academy of Sciences already. And they told me, okay, we received your documents, everything is fine, you're going to Italy. But you know, our Italian friends, they asked us to send us the text of your lectures before you come, so that they will be ready to understand exactly what you are going to talk about. And I asked them, when do you need these lectures? And they told me, better tomorrow. Okay, and I was at that time already kind of half dead. But I realized that if I do something, if I have some good idea, if I write it down, if I print it today on my typewriter, if I prepare it, it will go to Italy by diplomatic mail without any requirement of getting permissions or anything. So I grabbed my hand like that, and I said, moving, I said, what can I invent in half an hour, which I can type today and send it tomorrow as a paper so that it moves? What can I do in half an hour? What can I do in half an hour? I had a theory of eternal inflation. So that I got so excited. And I did not send the draft of this. I sent there some old materials, whatever. But months later, when I was traveling to Italy, I had 3 new papers on eternal inflation, which I smuggled and sent for publication from Trieste. So that was the story of that.
Thank you so much. This is this is incredible.
Yeah, well, yeah, I just wonder, should I specifically just, put myself to a state of depression? Yeah, to repeat, I'm not so sure. Okay, so my pleasure to give this talk, and thank you for your interest.
Thank you very
Thank you
much.
so
We're
much.
very honored.
Thank you.
Thank you.
Okay, bye.
Bye.
Thank you.